We have our fish data imported here. Let's start by taking a look at it in a scatter plot. We'll go graph, scatter plot. We want a 2D scatter plot. For our data, weight is our vertical or y variable, length is our horizontal x variable. Let's hit run. And we're going to see data that, well, it's pretty close to a straight line. So a linear regression model is going to fit this data pretty well, but there's a definite curve to the data. Okay, so let's try running a regression, a linear regression at first, a straight line regression, and let's use linear regression because that's the most straightforward way to do this. That'll also give us the residual plot that we would like. Weight is our dependent variable, length our explanatory variable, and we'll hit run. First thing we're going to see is a significant model, very significant model, with an R-squared of almost 95%. So this model fits our data pretty well, but not nearly as well as we can. Not nearly as good as we can do. If we have a look all the way at the bottom, second graph from the bottom, we've got residuals versus length. So our residual, our leftover, is on the y-axis, and length, our x variable, is on the x-axis. In the middle here, the middle of our data, between lengths, fish lengths of about 15 and 20 inches, we've got negative residuals. Remember, a residual is actual minus predicted. That's negative. That means our predicted value is greater than our actual value. We're over-predicting when we've got a negative residual. In these regions here, above about 20 inches, below about 15 inches, we're consistently under-predicting the lengths of these fish. And so it looks like we've got this pretty clear U-shaped pattern here, telling us, hey, we've got this at least one turning point in our data. It would be useful to do some polynomial modeling. We're going to start with a quadratic. Generally, we want to match the number of turning points to the number of terms that we have in the model. If we've got one turning point, we're going to want to add one polynomial term, one higher order polynomial, so a quadratic term. Looking at this, we've got a turning point here. We might have one there as well. If we do, that would suggest adding a third cubic term. Okay, let's see what we can do. We're going to pop over to do this in HP linear regression because it's a little bit more straightforward to do it in that. We won't have to create new variables. We can just do it within the effects modeling. So again, weight's our dependent variable, length our explanatory variable. But now we can explicitly tell Enterprise Guide to add in a polynomial. So we've got length and length squared, length times length. Hit run. And we've got an even better model. Our R-squared was around 95%, it's now jumped up to 99%. So we've eliminated, 80% of the remaining unexplained part of the data by adding in length squared. Length squared, very, very significant. Very useful variable in our model. Okay, if length squared is useful, maybe length cubed is useful. So let's try adding that in. Go modify our task, back to the effects tab, and add in a polynomial of length of degree 3 now. So length, length squared, length cubed. Hit run. Let's see if length cubed is significant. Yes, it is. What happened to our adjusted R squared? It went up. It was just a touch below 99%. Now it's 99.162%. So we've added on about 20% of the unexplained part of the data we've been able to explain with length cubed. Alright, if length cubed is useful, maybe length fourth is useful. So let's try that. Go to effects, length, polynomial of degree 4. So now we're adding length fourth. Hit run. And this time we're going to find that our adjusted R squared goes down. It was 99.162, now it's 99.156. So that suggests that we did bad by adding length fourth. And as we look down here at the p-value for length fourth, it's not significant. 0.6, much higher than our 0.05 threshold. So we did bad by adding length fourth. We should undo that, go back to having just length squared, length cubed in our model. Let me do that real quick because there's something else that I want to talk about there. Let's kill length fourth. The thing that I want to point out is I only looked at the p-value for length cubed. I didn't at length or length squared. This is standard for polynomial modeling. We don't worry about the p-values of the lower order terms, only the highest order term. If we have the highest order term, we must have the lower order terms. They're very much like the intercept in a regression. And so we just have to include them, even if they're not significant, and we don't bother interpreting them separately from length cubed.